Today I'm going to be pitching my operating system, Phobos Workstation, and the virtual computer that it runs on, tiny portable CPU. So here's the problem. Software doesn't last. Programs often have highly system-specific dependencies, and that basically means that, like, if I want to run a command line tool on Linux or something, oftentimes it connects to extraneous parts of my system that are really part of my distro. And if for whatever reason my distro has an updated version or has an incompatible version, it won't run anymore. And this is especially true for like C compilers like GCC and Clang. The libc that and the linker that your C compiler use are part of your distro, and it's very, very difficult to set up a C compiler inside of a directory and have it compile stuff, especially for cross-compilation. If you've ever set up cross-compilation with GCC or Clang, you know how much of a headache that is. Anyway, and so eventually, across years of time, what happens is that software eventually just becomes unrunnable. Right, and with GCC and Clang, it's maybe not as much of as big of an issue because there's a big community and even old versions have a lot of support. But like if we're talking about random old tools for like Windows 98 or something, these tools eventually become entirely unusable. And the thing is, this is really a big problem. There was a project run by this. I think he was an Australian guy who. He was trying to decompile a video game called Lego Island. And the thing is, lots of the tools he wanted to use were actually like really well-known tools back in the day. It's an old video game. But because of bit rot and because of all sorts of, incompatibilities and stuff, he basically couldn't get any of the software to actually work. And there were pieces of software in his toolchain, as I recall, that he was unable to run. Right, he was able to run some things, and the thing is, he had an immense problem, even with supposedly open source stuff, as I recall. I think he had problems with open source programs. I'm not sure, but I remember and this is just an example, right? When people want to work with old code or old tools, they very often run into walls where it's either extremely difficult to get a system set up that can actually run the tool, or it's actually impossible and no one can make it work. Anyway, and so the expectation with developer tools is that basically all a compiler does is it reads a bunch of files, it does some math, and then it spits out a new file, right? And that's something that can happen on any platform. So theoretically speaking, if I want to compile Linux for x86 64, right? If I want to compile an AMD 64 Linux kernel, and I want to compile it for a specific processor, I shouldn't just be able to do it from my system, which is an x86 64 system. I should be able to do it from my Nintendo 3DS. I should be able to do it from an iPad. I should be able to do it from basically anything that has enough memory to do that. Now, granted, maybe a Nintendo 3DS or an iPad doesn't actually have enough memory, but I think for the Linux kernel they probably do to compile the Linux kernel. So the thing is, it should just work, right? There's no reason why these tools should be bound to any particular platform. It's really stupid and ridiculous. All it does is it takes in a file, it does some jumbling on it, and it spits out a new file. It's very universal. It's something that should work on all systems. The reality, though, is that it's actually kind of impossible. If you want to cross-compile the Linux kernel from one platform to another, first of all, that means that you have to set up a cross-compiler, right? And that's a huge headache, right? And second of all, that cross-compiler might literally not exist on some platforms, right? So if no one has actually built a GCC that can compile x86 binaries for the Nintendo 3DS, then no one can cross-compile from the Nintendo 3DS to the x86 machine. You know, you know, that's a tragedy, right? It means that, you know, running a compiler is a very system-specific thing. I'd say that compiler tools might actually be harder to set up on a particular system and more platform-specific than graphics stuff, right? Like OpenGL. OpenGL programs run basically anywhere because basically every platform supports OpenGL. But if you want to run GCC or something, or you want to run a C compiler that cross-compiles, that's, you know, you're scratching at the wall, right? You're not. It's not going to happen on some platforms. Anyway, so what are some solutions to this problem? Well, people have come up with a lot of fake solutions, and I'm going to talk a little bit about why they're fake. They can kind of work a little bit, but they ultimately fall short of what we want here. So the fake solution one is to just put Linux on a virtual machine, and, you know, because you can have all the cross compilers you want on x86 on a virtual machine, and all the development tools and all the whatever, you know, you can basically put it in a box and then shove that on a hard drive, and then you have that forever, right? Well, there's a problem with that. The problem with that is after a long time. If you have a virtual machine that you've saved and archived somewhere that has a development toolchain on it, and you store it in your deep storage, and then 30 years later someone wants to use that toolchain again, and they pull out that hard drive and they try to plug it into a computer, well, you know, does the virtual machine software that you used back then even still exist? Does it exist for that platform, for the host? If it doesn't, can you implement a new one? I mean, obviously not, right? You're not going to be able to replicate these complex virtual machine softwares in 30 years, at least not reasonably, not at a reasonable price. Not an individual person almost certainly can't. And the thing is, even if virtual machine software does exist in the distant future, who knows if that virtual machine software is actually going to be compatible with the virtual machine software, with the virtual machine, that you saved 30 years ago, right? Now, this might seem like a contrived problem. Who the hell wants to use my tools in 30 years, right? In 30 years, computers are going to be so different, and no one's going to care. Well, in a lot of cases, that's actually true. Especially with enterprise programs, I can imagine that, like, you know, the existing weird corporate crap that's being used nowadays, no one will want to use in 30 years. Sure. A lot of it. But the thing is, especially when it comes to, like, video game preservation, old system software, and sometimes, I mean, like, sometimes people have, like, artistic works and files and stuff that they made on, like, old machines, and then, you know, they want to go back and look at it again, and they can't because the software platform doesn't exist anymore. So anyway, virtual machines are a fake solution, and by virtual machine I mean a simulated x86 computer or something, right? I don't mean like a language virtual machine. We're going to talk about that later. And this is an example of one. Java works better than a virtual machine, definitely, because I think Java will retain longevity over time a lot better. However, it's really hard to actually host an entire tool chain inside of Java, right? Especially an entire OS. Because if you really think about it, what you actually want to do to preserve a tool chain is you want to put your entire OS into a box, and then you want to package it away, and then you want to pop open the box again, run the OS, and then be able to use the tool. That's what guarantees that you can get the exact same experience using the tools the same way that you used to. So the thing is, Java can't really do that easily. A working JVM is possible to reproduce, by the way. It's really hard. And of course, there's intellectual property problems, like I say on the slide. You guys can read. I don't need to read the slide to you. If you actually want to try to implement your own Java, you know, and then try to put that in a box I mean, you could probably do it privately, as long as Oracle doesn't know about it. But if you're an individual person and you want to publish it online, you want to publish your own Java implementation, you might face some problems there. So there's some intellectual property problems. But with the thing about an entire OS, that also, guys, might seem a little contrived to you. Why do I want to put in my tools into an OS, right? Why is that necessary? Well, if we go back to years of time, if you think about what happens across years and years of time of bit rot, basically, what happens is that the various pieces of software that your tool interacts with on the operating system are also changing and updating and stuff. So in order to preserve your tool, you need to preserve not only the tool that you used directly, you need to preserve the tools around it. For instance, if you use a compiler and a linker and a C preprocessor and a shell, you use a shell and you use a make program, and maybe you use you use one of these complex build systems like Ninja or whatever, then you've got to preserve all of that. You've got to preserve all of it so that someone can just pop open the box, press a key, and get the build to happen. And that's basically what you need to have in order to guarantee that software will still work 30 years from now, 20, 30, 50 years from now. So virtual machine doesn't work. Oh yeah, by the way, it's bloated. You're actually storing a huge amount of data just to get your tool chain working. And part of that is necessity, but a huge part of it is just bloat. If you take your average Linux distro, even like Alpine Linux, you're probably packing in way more megabytes of information into your thing than you really need to. And this is especially problematic if you're doing tons and tons of backups that are fully usable, right? If you're doing that, you're wasting a lot of space. And so we talked about Java. Fake solution 3 is just to write it in Lua or Python or JavaScript or something. Here's the thing. Just like I said, the software that your software depends on is part of the dependency chain. And when that software updates, it's completely out of the blue, right? So if you just write your tools in Lua, Python, or JavaScript, that's not actually a good solution, because then you also have to maintain the Lua program or the Python program or the JavaScript program. And then when you really think about it, when you think about all the stuff that you need in order to get that to happen, you end up with like an entire Linux distro. And so this is not really a good solution. So the fourth fake solution, right, and this was one that almost works. This was actually a really, really close one. RISC-V emulation. Now, you might have seen this thing that went around on YouTube a while ago, but basically some guy figured out how to make a really tiny RISC-V emulator, and he made it run Doom and stuff. Basically, the way he did that was he did not implement the memory mapping unit, and I think it was also integer only or something. I forget, but basically, it was a super limited version of RISC-V. And the thing is, yes, you can make Linux run on it. You can even put your tools on it. But it's really slow, first of all, because RISC-V was designed to run on real silicon. It was not designed to run inside of an emulator. It was not designed to emulate fast. And so RISC-V emulation is going to be slow. And it's also, if you're putting an entire Linux distro in a box, that runs into that same problem we talked about, which, an entire Linux distro is really big. So you don't really want to do that. It's a lot of work. And so this is actually really close, and this is the closest thing probably, apart from like this one here, to what I'm doing with my operating system with my operating system Phobos Workstation and my architecture TP CPU. The fifth fake solution is Oberon A2, and so this one is also really close, but it's still not it. It can run a real OS. It can and does run real tool chains, but the amount of implementation overhead of actually writing an Oberon emulator, it requires an x86 emulator, which is really hard. The way that you actually get it running on Windows, I'm not actually able to run Oberon A2 on Windows. I tried running it, and it doesn't work. And Fake Solution 6 is Uxin, right? And Uxin is actually almost exactly right? It gets everything nailed down. It's very similar to RISC-V in that regard, in that it's a virtual CPU architecture that's fairly easy to re-implement from scratch. However, this one runs fast. Uxin was designed to be emulated, but its address space is tiny. It's only 64K. It only has 16-bit math, so it's not actually going to run any of that, do any compilation really quickly. And it lacks the fundamental capabilities to run a real operating system. RISC-V, by the way, if you implement RISC-V without the MMU, which is how that guy did it, and to get it small and get it manageable, if you do that, then you're actually implementing a gimped version of RISC-V that technically can, yes, run Linux, but it doesn't have any memory protection, and if it crashes or whatever, it'll crash the entire OS, or, well, it can, right? Anyway, so the real solution, the thing that we actually need is we need a virtual CPU architecture that is easy to re-implement, can actually has the capabilities to have an entire operating system on it, right? It needs to be able to have all the tools and stuff. It needs to have the memory protection and preemption, like it says on the screen there. It needs to have the address space. It can't be like Uxin, where you're literally only addressing a Commodore 64's worth of memory. It's absolute, crazy to think that anyone could actually use that for anything more than toys. And it needs to be something without intellectual property restrictions. In this case, this project I'm working on is fully public domain, CC0. There's no restrictions on it, and it should be designed to be emulated fast. And that's what this project is. Also, on top of the CPU architecture, I'm running an operating system. And I'm calling it a full computer, but in reality, I'm calling it an operating system too, right? It's the line there is blurred. What's the difference between a computer and an operating system when we're talking about virtual computers? And I'm not sure there actually much is one. I'd say Phobos Workstation is an operating system for the virtual hardware of TP-CPU, and thus comprises a virtual Phobos Workstation personal computer. Basically, Phobos Workstation is all of the above, right? It's a tiny little operating system, very, very small, right? So if we actually look at the size of the entire OS is less than a megabyte. And that's just that is obviously without your tools in there, without your compiler, without your stuff, right? But it all fits in this tiny space, And it's a tiny computer that's easy to re-implement. It's fully public domain, and it can actually do the thing, right? It can actually run a real operating system. It can multitask. It can protect memory. It can guard memory overwrites so that one program does not overwrite the memory of another. And so the project goals, the goals for this project, TP-CPU and Phobos Workstation, are to preserve software and document software, right? I'm also thinking about TP-CPU and Phobos Workstation as a way to document algorithms for future generations. This is a way that educators can store algorithm examples or implementation examples for students. If you are someone who wants to design a new amazing programming language, and they want it to be preserved in a way that other people can study and re-implement for you by studying your implementation, TP-CPU is a good place to show a demonstration of your compiler or whatnot. It's a good way to make sure that things last and are studyable and analyzable and stuff. Another goal of mine, right, is I want to be able to have the entire I want to have, any computer basically be bootstrappable. Any capable computer be bootstrappable into a functional development environment. So if any computer has enough RAM and it has the disk space and it's fast enough, then I want to be able to take that computer and I want to turn it into something that can run arbitrary. I can turn it into a programming environment, right, where I can write code and compile stuff and things like that. And I believe that's very doable. I think that basically any computer with the capabilities should be able to be a development environment. It should be, a place where you can compile code for itself or for other platforms and run it. Run it if it's on the same platform. And I guess we could talk a little bit about maybe you could host emulators on TPCPU in order to be able to test software for other platforms, but that's another issue. Emulator within an emulator is kind of iffy, but you could do it. It would be in the vein of software preservation, but it would run really shit. Anyway, and all of this, I want to do it in the public domain for maximum utility. Now, this is another thing you guys might be wondering: why public domain? Why does it have to be CC0 instead of MIT or BSD or whatnot? And well, part of it is principle. I don't believe that intellectual property, as it exists right now legally, is, well, to be frank, I don't think it's consistent or coherent, so it doesn't really exist, but it is nonsense, and it's oppressive. I think it's fundamentally wrong in many ways. So I don't want to take part in it. That's part of it. Another part is that there are actual problems with open source software licenses, open and free and open software licenses, like the MIT, like the BSD, and yes, like the GPL and whatnot. Part of that is attribution. If your license requires attribution and then hundreds of people contribute to the project, suddenly that's hundreds of names that you have to list in a file somewhere in order to be able to share the software. And that's a burden that I don't want to place on people. Another part of it is that legal text is not very easy to interpret, and when people read legal text and they see something like this notice shall be preserved in any substantial portion of the software, they are asking themselves, do I have to ship it with binaries? Under what circumstances? How do I display the notice? And so they're very worried about, maybe I'm going to be accidentally breaking the law when with this complicated license that says all these complicated things about notices and attribution and whatnot, and the licenses don't make it clear. It's not clear, so it's a bad thing that your code has to have this license. It is an anti-feature. Okay, it is wrong. And this applies to the GPL too, by the way. Even if you make your code GPL'd, right, and let's say that you don't require personal attribution, you donate it to the GNU project or whatever, that's still a huge problem. The thing is, there's stuff in the GPL, especially the V2 and V3, where it's very hard to figure out what it actually wants from you. What is the editable source code? What source code is it talking about? Does it literally always mean the source code that I wrote by hand? Okay, but what if I use a tool to modify the source code? Do I have to publish the tool? And then there's other issues, right? Like with the GPL v3, the anti-TVOization stuff. What does that mean? How do I actually do that in practice? And of course, if you ask the GNU people, they think they understand what it requires, but will lawyers in 30 years have the same opinion? I honestly don't know. And I don't think they know either. So I think it's really crap. They should just try as hard as they can to put it into the public domain like I have. I just use CC0, which basically says do whatever you want. The only thing you can't do is you can't try to patent or copyright it so that other people can't use it. You're not allowed to patent it or copyright it or whatever and make it like personally yours so that other people can steal it. Anyway, so let's talk a little bit about the roadmap, right? The general roadmap is in two major phases. The phase one is the one that I consider like the real project. It's the project that TP-CPU is actually kind of built for. It's kind of saleable as, right? Where basically what people will be doing is they'll be taking command line tools and then porting them to TP-CPU and then be able to just run them inside of TP-CPU. And that's what phase one is for, so that you can preserve compilers and file utilities and stuff that aren't being preserved right now, right? And that's what I imagine that is for. And phase two is a graphical operating system. And the idea of the graphical operating system is mainly this. I want to be able to have any computer be bootstrapped into a functional development environment. Which you'll notice I didn't really talk about here because basically I haven't gotten to that point yet. In order to get to this point, I need to complete phase one, and then I can work on phase two. But basically, phase two will be like I want to design a desktop operating system and work all the kinks out of that, right? Or at least a graphical operating system of some kind, right? It doesn't necessarily need to be a desktop operating system, but it probably will be if I want it to be useful and powerful. Because the thing is, if it's not a traditional like Windows style operating system, it's not going to be easy to port tools to it. That's first of all. Second of all, it's also going to be questionable how you actually build work environments on it, right? How do you do the traditional compile, text edit, loop if you don't have Windows? Anyway, so the phase one checklist roughly is that first of all I had to design and implement the CPU architecture, and I did that. I made a kernel, and I worked a long time on that, and I basically done that. I also had to make an assembler. I had to make an initial assembler in order to create the kernel, but then I also had to make an assembler that runs on the platform, and I did do that. I made a shell that you could run on the kernel, which is basically just if I can boot it up here. Oh, hold on. So this is my shell, right? It has commands, right? It has some built-in commands, and then it has these commands that I've made for it, right? And I needed file copy / delete, right, and other file utilities, so like del, that's the file delete, mv, that's the file move. And by the way, the move, delete, and copy are recursive. They actually can copy whole directories. And I need high-level language compiler support. And I only have one language that can compile the TP-CPU assembly right now. But I'm talking with a guy who may or may not be writing a C compiler. If he does get the C compiler done, that will enable me to hopefully port over some other languages. His C compiler won't be a native toolchain. It will be a cross compiler, but it should enable me to compile programs to TP-CPU assembly from C. Right? Coder's Basilisk, by the way, is my C replacement. It's just that there's not much software written in Coder's Basilisk. What I can do with a C compiler is I can take C software that already exists, and I can modify it a bit and eventually get it running on Phobos Workstation. And I need documentation, and I've partially done that. Right, I've done this. Right, there's been 50-something pages of documentation so far. There might be some blank pages in there, but yeah. And that's the phase one checklist. Now for phase two, I'm just not there yet. In order to be able to do phase two, I need to be done with phase one. Now in terms of the release schedule, right? I don't really have a schedule per se, but I'm hoping that I can complete phase 1 to a reasonable degree this year. That TP-CPU will be capable of hopefully at least compiling 1 or 2 high-level languages before the end of the year. It has an on-platform assembler, so as long as you have so you can write programs on the platform for itself right now. But the thing is, it doesn't have any ability to. It doesn't have any high-level languages that work on the platform. And longer term, phase 1 would also eventually encompass maybe getting some cross-compilation tool chains working, but that would be a huge jump. I'm not planning on doing that in the main repository. I might. What I might actually do is I might. After I do phase 2, I might then do a call out where I ask people to develop cross-compilation toolchains that run on TP-CPU, like x86 compilers that run on TP-CPU. So good, phase 2, not there yet, but in general, the direction I want to go with the graphical OS is probably a desktop environment, kind of like Windows, but done in a TP-CPU way. So like a greater emphasis on simplicity and ease of programming and portability, right? So it's for instance, I'm probably not going to do hardware acceleration. It's probably just going to be software rendering, because I don't want to require implementers of a TP-CPU emulator to. I don't want them to have to write an OpenGL implementation in order to get the system working. I want to thank you guys for watching. You can find the project here or here. Right. So this is it on GitLab. I just edited the project settings so that you guys should be able to see it. And then there's the project on Codeberg. I don't have it on GitHub. That's because I'm not on GitHub. So yeah, if you want to access this software, you can get it from these 2 places, and it's public domain, like I said. So if you want to fork it, if you want to, if you just want to steal it, you can. In fact, that's kind of encouraged. You don't have to credit me if you don't want to, but I would like to be credited. I would like to be given thanks, but you don't have to. You don't have to. Basically, if you care about the software, you credit me, and if you don't, if you're a jerk, you don't. But I'm not going to call the police because you're a jerk. You're just a jerk. So that's that. Hope you guys enjoyed, and thanks for watching this video.